Welcome to The Explainer. Today, we're taking on a concept that, honestly, at first glance, feels completely eerie, kind of magical, and almost beyond human comprehension. We're talking about artificial intelligence. Specifically, that uncanny ability of machines to just look at visual information and seemingly understand it, exactly like we do. It's what we call the ghost in the machine. When a computer recognizes a handwritten number or, say, identifies a face, it really feels like there's a ghost inside the circuitry, right? Like a spark of real, living cognition. But our goal today is to shatter that illusion and replace that magic with actual understanding.
Okay, let's dive right into our roadmap for today. We'll explore the ghost in the machine, see why AI is just math, understand how a network learns, uncover the magic of backpropagation, and finally, look at seeing through the numbers.
All right, kicking things off with Section 1, the ghost in the machine, an illusion of magic.
So this is where we really need to address the elephant in the room. There's this massive contrast between how we view AI versus what it actually is under the hood. I mean, we've basically been conditioned by sci-fi to view artificial intelligence as this mythical entity, a ghost, or some autonomous brain that somehow just sparks to life. That's the myth. But the reality, the gritty, unglamorous truth, is that it relies purely on the rigorous application of mathematics. I hate to break it to you, but there are no spirits in the server room. There is literally only calculus and linear algebra being applied to massive, overwhelming amounts of data. It's a total shift in perspective, going from expecting a wizard's spell to, well, examining the gears of a really intricate clock.
Which brings us to the core mystery of our explainer today. How does a neural network actually see a number? Think about it. When you or I look at a handwritten number 7, we just know what it is instinctively. Biological sight relies on billions of years of evolutionary intuition, right? Our brains effortlessly decode shapes and edges without us ever having to actively think about it. But a machine doesn't have eyes, it doesn't have a biological brain, it just has a completely blind grid of pixels. Drawing on the brilliant visual intuition popularized by 3 Blue 1 Brown, we're going to break down how machines manage to interpret this purely digital information. Like, how on earth do they take a dead grid of pixel values and translate it into absolute certainty?
Let's move on to Section 2 and see how this builds. AI is just math, the tools of the trade. Now, when we strip away all the flashy, futuristic terminology and ask what foundational architecture AI is actually based on, well, the answer takes us right back to classic mathematics. So, before we can truly understand how the machine is built, we need to know exactly what tools are inside the toolbox. Any guesses on which branches of math we're talking about here? If you guessed linear algebra and calculus, you hit the nail on the head. These branches of math act as the actual physical cogs and wheels of our machine. Now, inside a neural network, these mathematical fields take shape through two very specific mechanisms: weights and biases. Think of weights kind of like the volume dial on a specific clue, amplifying or muting different pieces of data. Biases, on the other hand, actually scratch that. Think of biases more like a minimum volume threshold that has to be crossed before the network even pays attention. Together, driven by all that calculus and linear algebra, these weights and biases operate on just staggering amounts of data, constantly shifting and adjusting. They are the actual, literal mechanics behind artificial cognition.
Which brings us to Section 3, how a network learns, the assembly line.
And this brilliantly illustrates the mechanical heart of our explainer. This is where we watch those mathematical tools get put to work in a continuous, flowing sequence. I want you to imagine a single data point entering a giant mathematical assembly line. First up, the raw pixels are fed in as an input image. Then, as that data moves forward into the network, it calculates weighted sums, basically tallying up the math based on those internal weights and biases we just talked about. But before moving to the next layer, an activation function steps in. It acts as a gatekeeper, deciding if that tallied information is actually strong enough to trigger the next step. Eventually, this whole cascade of math produces a guess, which leads to a reality check, a comparison with the result, where the network's guess is checked against the actual correct answer. And finally, if the guess is wrong, we hit backpropagation. See? This isn't abstract magic at all. It's a precise, step-by-step mechanical process that perfectly simulates human-like recognition.
Moving right along to Section 4, the magic of backpropagation, the climax of learning.
So, we know the final step of that assembly line is backpropagation. Everything before this, that was just the network making a guess. But what exactly is backpropagation?
What is mechanically happening inside the machine at this exact pivotal moment when that guess gets checked?
Listen, this right here is the absolute key to artificial intelligence. Backpropagation is the method by which a neural network adjusts its weights based on its errors. When the network guesses wrong, backpropagation uses calculus to trace that error backwards through every single layer of the network. The system identifies exactly which weights and biases contributed to the mistake, and it modifies those internal settings. It just nudges the numbers slightly so that next time it'll be a little more accurate. Without this specific mechanism, a machine literally never gets smarter. It would just be a static, boring computer program. It's this elegant, continuous loop of self-correction that ultimately gives us the illusion of a ghost learning from its mistakes.
And that takes us to our final section, number 5, seeing through the numbers, the final payoff.
So the crucial point is this. In the very beginning, an untrained neural network is completely full of initial mathematical errors. It's just guessing blindly in the dark. But by running massive amounts of data through that assembly line and constantly applying that loop of backpropagation we just discussed, those layers of weights and biases are finely tweaked. Those initial errors are steadily ironed out, resulting in profoundly improved accuracy. The network eventually becomes so incredibly accurate that it mimics human cognition seamlessly. But as we now know for sure, it isn't magic recognizing the number 7. It is simply thousands of tiny, perfectly calibrated math equations, essentially a high score of calibrations, all working together in perfect harmony.
We started today by talking about the ghost in the machine. And I think we've proven that the ghost is really just an illusion created by calculus, linear algebra, weights, and biases. But, it leaves us with a truly fascinating question to walk away with. If the deeply impressive human-like cognition we see in AI is fundamentally just complex math and error correction, what does that say about the math behind our own minds? Are we, too, just a brilliant biological assembly line of weights and biases? It's definitely something to think about. Thanks so much for joining me on this explainer. Keep asking questions, and I'll see you next time.